Hey, good morning, guys. We're going to do a couple application problems, probably just really one today and one tomorrow, and then we should be ready for our test or ready to review for the test. But these are called special differential equations, mainly because if you think back to Algebra 1, there was a thing called direct variation. And direct variation equations were basically they gave you an ordered pair and they said relate x and y directly. And what that means is there's a model to write the relationship between two variables that vary directly, that vary inversely, and that also vary jointly. But I don't believe we'll do any joint variation as much in this class because it's multivariable calculus then. But direct variation means that there exists some constant k that makes two variables equal. For instance, acceleration / force problem. The acceleration of an object is directly proportional to the force acting on it. Okay, to write an equation stating this relationship, what we're going to do is we're going to say our acceleration, is directly proportional to the force acting on it. And like I said, there's some constant k that I can multiply times my force. There's some constant, and k is a constant, that is going to make a and f equal. Okay? That is going to relate a and f and make an equal statement for that. So this is what we're going to be working with, and if acceleration varied inversely with the force acting on it, I would have acceleration equals my constant divided by the force, because inverse variation was basically division. This is inverse variation, and this is direct variation. Okay, and I don't want to get too tangled up in here, but back in Algebra 1, basically, when we related two variables, and the k is like the slope here in a direct variation problem, basically, but suppose a force of 80 newtons causes an acceleration of 7.5 meters per second. Write the specific equation for this problem. There's no calculus involved in here. However, all I'm going to be doing is I'm going to say, okay, suppose the force is 80. What is my constant k that gives me my acceleration of 7.5 meters per second? So k would have to equal 7.5 divided by 80. So my k is approximately equal to, if I round this to 3 decimal places, it's 0.094. So the equation that relates a and f is going to be a equals 0.094 times the force. So if I multiply the force by 0.094, I will get the acceleration, okay? And then they're going to have you work with it a little bit, and that is no more than what force would cause an acceleration of 9 meters per second squared. Well, here is my acceleration. That's going to equal 0.094 for my force. So if my acceleration is 9.0 meters per second squared, my constant of variation is 9.4. That means my force is going to be basically equal to 96 newtons. Okay? And again, I didn't use any calculus for this problem. And here, I'm not going to go through this whole problem, but the main thing is being able to write a direct variation problem. The speed of an object is directly proportional to the square root of the distance it has fallen. So we need to pick some variables. So my speed, I'm going to call s, a fancy little s, is directly proportional. That means I have some constant of proportionality. We're going to call that k. And k is a number. It's not a variable ever in these problems. To the square root, well, if I call distance d, it's going to be proportional to the square root of d. Okay, so that would be my constant, that would be my direct variation equation that is relating speed and distance. And if I had a particular speed and a particular distance, I can calculate that K value, all right? And I'm not going to waste time to do that in this problem. We're going to move on because the main point is you need to be able to write your direct variation equation. And then from there, we are going to use calculus on it. So let me have you recall here exponential growth and decay. And back in Algebra 1 and Algebra 2, we had some A value here where our growth kind of, we grew. This is a growth problem. And we also had a decay problem. And that decay problem had a y-intercept, and that decay kind of came down, got snug as a bug in a rug, down to that horizontal asymptote, and that was a decay. And when we used these back in Algebra 1, we actually wrote equations of these. And this first one looked like y equaled some initial value. This is 0, comma a right there. Okay, some initial value times b raised to the power of x. And if it was a growth problem, remember, b had to be greater than 1 to make it grow. Well, if it was a decay problem, I had y equals some a value times b to the x. And again, this is my initial value, 0, comma a. But when I was on a decay function, if you recall, b had to be greater than 0 but less than 1, and it could not be negative because then it was no longer an exponential function. And then we worked with that just for a little bit, and we took both of these growth and decay functions and we wrote them into one. We wrote them both into a base e exponential function, which is like y equals some a times e to the kt, k times t power. Okay? And how did we write growth and decay both into this exponential function? Well, we changed the base on it, but basically, if k was greater than 0, right, that gave me a positive exponent, and that was growth. And if k over here, if k was less than 0, hey, that meant I had a negative exponent, then it was decay. And we could control growth and decay all on our base e. And remember, our e is approximately equal to 2.7128-ish. I'm just going to call it an ish. And bottom line, that A was still our initial value. And if I try to relate this to what we've been doing, maybe, just maybe, our function we're going to look like is going to look like y equals some initial value c times e to the k times t. And this is what we're going to be getting after. We're going to be generating that equation of both exponential growth and decay all through word problems, okay? So let me come to the next one. Laws of exponential change in calculus. Well, exponential growth or decay, okay, either one, in which the rate of change, okay, we have a rate of change. We can really call that y prime, and we're going to call it something different than that, but where the rate of change is directly proportional to the amount present, okay? So what does that mean? That means the amount you have is directly, the amount you have now, the amount you had, your rate of change is directly proportional to the present amount. Well, if y represents the amount present, the differential equation that's describing this particular situation is, okay, because bottom line, it's a differential equation, so we're going to use our y prime as dy dt, okay, and we're going to, because the amount of something you have present is related to time, but we're going to use differentials, dy dt, instead of y prime, is equal to k times y, okay, where the rate of change of y is directly proportional to x. And what that's going to lead us to basically, if I took this out of differential notation, y prime equals k times y. And this is going to make you think, hey, whose derivative is the same thing we started with? And that would have been an exponential function, right? The derivative of e to the x is e to the x. And so we're going to keep on a trucking here. And what do we got? Where k is a constant, is a growth or decay constant. Okay, this is a big topic right here. K is not a variable. It's not a variable. It is a constant. And we are going to find that constant through these special differential equation problems, okay? So let's solve this differential equation for y. So if I have the rate of change of y is directly proportional to the amount that's left, okay? The rate of change, that's my dy dt, is directly proportional to, that's my constant proportionality, directly proportional to, is going to be k is going to be multiplied to my amount present, and y is the amount present. So my dy dt equals some k times y. And what we're going to do, we're going to solve this differential equation for y now. So if we did that, well, first thing we need to do, because we're looking at this, hey, we better separate our variables, just like we had been doing. So if we take this side times dt, this side times dt, well, I really have dy equals k times y dt, okay? And then you're going to actually multiply both sides by 1 over y to separate those variables. And I get 1 over y dy equals k times dt. And remember, k is a constant. Okay, it's hard to think, but k is a constant. Is it always a constant in these problems? Most definitely it is. And then we solve for y like we did. We separate, and then we integrate. Okay, so then separated the variables. That gave us our green light to integrate. Well, what is the antiderivative of 1 over y? Well, that is the ln absolute value y equals, the antiderivative of a constant would be k times t plus c, plus my constant proportionality, or my constant of integration, I'm sorry. And then we take this and we solve for y. Well, we know how to do that. How do you do that? Well, we can just rewrite this thing because logs, or we can do what I've been doing before. I can say, hey, I can base e both sides, and it gets rid of that, so I get y equals e to the kt plus c, bad t. And we always wanted to find c. Well, we can't find c here, but remember, y equals e to the kt, like we've been doing, times e to the c, where this e to the c is just a number. Therefore, y equals that c value times e to the kt, and we get our direct variation equation problem actually turned into laws of exponential change in calculus. So our direct variation equation turns into an exponential equation when we integrate it, and hopefully that makes sense. So how are we going to have to use this over the next day or so? I'm only going to do number 3. I'm going to do all of number 3. Have your calculator handy. There's some things you're going to have to learn about your calculator. And in calculus, a variation problem is worded as follows. Exponential, this is an exponential growth problem. We will do an exponential decay problem tomorrow, and then we'll do one that's not even growth or as much decay. It's just kind of randomly out there a little bit. well, it is kind of, but we'll get to it. But a certain type of bacteria increases continuously at a rate directly proportional to the number n present. Okay, so n is the amount. It's the amount of bacteria. It's hard to write on this board. Present. It's, I don't even have to say present. It's the amount of bacteria at any time. Okay, I'm just going to call it that. It's the amount of any at any time. But we want to write a differential equation stating the relationship between the rate of change and the number of bacteria. Okay, the rate of change. Hold on, Trevor, back this up. I gotta get this all. This is all one part here. We're writing the rate of change of the number of bacteria, okay, and the amount of bacteria present at any time t. Well, what does that mean? Well, what is my rate of change of bacteria? That would really be, if I don't use a differential equation, that would be n prime, wouldn't it? That would be the derivative of my bacteria equals my constant directly proportional to k times the number n of bacteria. But this is not a differential equation. Why? Because it doesn't have differential. So we want to say dn dt equals some constant k of proportionality that we are going to find times n. There is our differential equation stating the relationship between the rate of change of n and n. Okay, again, whose derivative is the same as what you basically started with. It may vary by a constant, but an exponential function. Okay, so then what we're going to do is we are going to solve the differential equation to find the amount of bacteria n as a function of time. Well, that's not too bad, okay, because as I'm separating my variables, remember I want to get all my n's on one side, I want to get all my t's on one side, and remember, this guy is just a constant, and we typically, not typically, it's easiest to leave that constant on the right side. So if I leave that constant over there, and I get my dt over there, right, I'm going to multiply this side times dt, I'm going to take this side times dt, that's getting rid of my dt's. Then I need my n over there, so I might as well multiply this side by 1 over n times 1 over n, so I get 1 over n, whoop, with my dn on there though. I get my 1 over n dn equals k dt, because this is going to cancel, and I have separated my variables. After my variables are separated, what do I want to do? I want to integrate, okay? Right now is where we are showing our calculus through our separate and integrate. Well, what's this going to give me? This is going to give me the ln, absolute value n, equals some k, antiderivative of constant is a linear term, plus constant of integration. And then what we're going to do is, hey, they want us to find the differential equation as n as a function of time. That's how I knew it was time here too. So then what do? Well, I'm going to solve it for n, which is going to give me n equals e to the kt plus c. And you don't have to separate those variables out like we've been doing. From here, you don't have to show that next step if you know n in terms of time is going to equal some constant. My beginning amount, see that c, that is just like my a value, e to the kt. This is just exactly like it was in Algebra 1 or Algebra 2, where we had y equals some a times e to the x, okay? And they're the exact same. Beginning amount, initial amount, beginning amount, or initial amount is my constant C. So then what are we going to do? We're going to take this constant, okay, and we're going to take this n in terms of t equals C e to the kt, and we're going to use this information to find the particular solution of this differential equation. And suppose there's 100 present at a given time and 300 present 5 hours later. Well, that means when t equals 5, n, or n of t, or y equals 300. Well, suppose at some time there's 100 of them. Okay, well, what time is there 100 of them? Well, it doesn't matter when it is. Suppose there's 100 present. When? Well, when I'm kind of starting my study, or when I'm starting this thing. So my initial value here, okay, I got to find a value for C and K. And in order to do that, I would probably want to use this initial condition first, because then I can say, well, n of t, that's 100. Equals C e to the power of 0, so I know C is 100. Well, Mr. Kruger, if I knew this was my initial, my initial amount, and I knew this went to n of t equals 100, boy, look at that. Got to really write slow on this thing. N of t equals 100 e to the kt. If I knew C was 100 back here because of this initial amount, do I need to show this work? Absolutely not. Now what are we going to do? Well, now we're going to use our other condition here so we can find our K value. Remember that K value, that's going to be our rate of decay or growth. And I think this was what? This was a growth problem. So our K value better be a positive value because it's growth. But all I got to do is plug in my 300 equals 100 e. Well, time is 5, so that's going to be 5K up there. Okay? And you do know how to solve this algebraically because you're going to divide both sides by 100 and you're going to get 3 equals e to the 5K. Oh boy, how do I do that? Well, you could rewrite this, remember, because logs with a base e equal exponents, and there's my 3, so my K value equals the ln of 3 divided by 5. Well, what does that mean? Well, that means my function, n in terms of t, equals 100 e to the ln 3, oh boy, that's bad, 3, ln of 3 divided by 5 times k. Okay, that is my function. Okay, that is my particular solution to this equation, and I want you to know that it would be a good answer on the AP test. Also, this is the next thing you need to know. Using your calculator here, okay, what is the ln of 3 divided by 5? So you open up a calculator page, hopefully, and we say ln 3, and we get out of there and we say divided by 5. Well, what is that as a decimal? Well, it's 0.220 if we round it to accuracy as for the AP test. So we would say this is also equal to 0.220. So another function particular solution that would be okay would be 100 e to the 0.220 t. And this top one up here, K is that, and it's a function of time, so I need my time in there. Either one of these would be perfectly acceptable to report for your particular solution. However, if you have to use this down the road, you must use the exact value for K. You cannot use the approximated value for K because you will run into rounding error. What are you talking about? Well, what I'm trying to tell you is you are going to need to be able to type this into your calculator and store this value in there. So here's where you're going to take your calculator. Okay, I can do this, and if I wanted to store this number in my calculator, that 0.219722, blah, 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 and it keeps going. If I wanted to store that, right above number 9 is a VAR, and right above there, if you hit Control Var, it's going to ask me to store this last answer, that decimal. I want to store it into, I can store it in any letter I want down here. I am going to choose K because that's what it's called in my equation. And then I'm going to hit Enter. And now anytime I come through, anytime I hit a K and I hit Enter, it's going to replace that in my equation with that. If I wanted to know what 2 times K was, it's going to multiply it by 2 anywhere it sees that. And notice when I hit K anywhere, notice it's a boldface K. It's not the italicized K. Whenever your variables come up boldface like that, there is a number stored in it, okay? So we want to be able to use that value in our equation to find an exact approximation, not even to find the exact amount that's left. They do not want it rounded for your final answer, okay? So we're going to come here to the next problem, plot the graph as the amount n as a function of time. Well, that's kind of a no-brainer there. That wants me to graph n in terms of t, where I start at 100 and I go e, I'll put a parenthesis there, and I want e raised to the ln, I'm going to have room here. Raised to the ln of 3 over 5 times t. They want me to graph that, but they don't want me to graph that with the decimal. They want the exact graph. Well, if I did that, this is my n-axis, this is my t-axis. I do know my initial amount here is at 0, 100, and I do know it's a growth function, and it's going to grow, so that would be good enough for this, okay? And if they wanted me to know how many will there be in 10 hours after the initial time, well, they want me to find n of 10, okay? And that's going to equal 100 e to the k times 10. That's why I went back and I stored that k value, that exact value, in my calculator. So I would come back to my calculator, and I would say, what is 100 e to the k times 10, enter. Oh, there's 900, exactly 900 bacteria. So I would come back here and I would say 900 bacteria. I would say equals my n of 10. Okay? And if I didn't use that exact value, and I know a lot of you are going to say, well, that's stupid, but if I didn't use that exact value, and I took my decimal, and I took that decimal of 0.220 times 10, okay, and I hit enter, hey, now I'm going to get 902.5 bacteria or 903, and that's not acceptable on our test. So we need to learn how to store that value right there. We need to know how to store that k value into your calculator, okay? And that's pretty important to do. And let me back up one quick second here too. Say, oh crap, Kruger, I forgot how to algebraically solve this log right here. Well, if you forgot how to solve this thing, remember you have solver, okay? And what you can do is anytime you store a number in terms over the top of k, okay, you'll have a new number. So let's come back here. let's grab this. And remember, that's a menu algebra solve. And I'm solving 300 equal, whoa, what's going on here? I'm solving 300, delete, delete, delete. I need my menu algebra, I need my solver, and we're solving 300 equals 100 e to the, what was it, 5k, wasn't it? Equal to the, but I can't use k here because I've already stored a k in there. Watch, if I hit a 5k, see, I can't do that. I'm going to have to maybe call that a t value, okay? And then I'm going to come out of here, and I got to tell my calculator, please solve it for t, and it's going to say, hey, there it is. And then I can take that value, and I can say, let's please store you in terms of k, all right? And anytime I now hit k, it's going to store that exact value for t in there. And then if I had to come back and I had to find 100, control, no, not control, escape, 100, oh, if I needed my 100 e to the k times 10, it's going to reach out, it's going to grab that k, it's going to grab it, and it's going to give me my exact, what's going on here? Let's sort it in for t. Hold on. Okay, when I went back, I noticed when I used my solver, I never got my, I don't think I got my store. So I'm going to hit enter, and I want to take that, and I want to store that answer into hopefully k. I'm going to hit enter, and then if I type a k and hit enter, well, now it gives me the t equals. So I really don't want the t equals in there. So I think it's still going to do the same thing. So you want to be able to type that ln3 divided by 5 and get a decimal. Okay, so when I use my solver, I guess I was mistaken because it's throwing t into the equation when I store it. I'm going to want to be able to take that ln3, and I'm going to want to be able to say, all right, control. I want to be able to take my ln3, and I got to divide ln3, and I got to divide that by 5. I got to get that, and then I got to store that last thing in my k variable, and then it'll work. 100 e to the k times 10, and then it's going to give me my 900, but I have to take the t out of there, okay? And then the last thing they're going to make, sorry, I hit the wrong button. The last thing they're going to want me to do here is, as I chunk along here, is they are going to want me to get rid of this. How long did it take for the number of bacteria to double? Well, remember, we know k equals the ln of 3 over 5. So if we started with 100 of them and they doubled, there will be 200 left over. There's no calculus involved here. These are just like your pre-calc problems. This is going to be e to the ln of 3 divided by 5 times t. That's what we're solving for. We can algebraically solve that, or we can just use our solver here. Let's use our solver. I'm going to grab my calculator, and we are saying menu 3.1, menu algebra solve, 200 equals 100 e. And now I should be able to use my k in there. See, it's bold, times t. And I'm going to put t in there. And then I'm going to arrow over, and I'm going to say, please solve for t. And I'm going to hit enter. And it's given me a gross one. And if I don't want that, then I come up, if I want the decimal, then I hit control approximate, and I get about 3.155 hours. Okay, and I solve that with that, and I come up with t is approximately equal to 3.155 hours. Okay, but it is really important that if you're using this equation to calculate anything after you've generated it, it's really important to use the exact value of k. Otherwise, you hit your rounding error. Like menu 31. Whoop. Escape. Come on. Delete. So if I hit my menu, algebra solver, and I try 200 equals 100 e to the 0.220 times t. Solve for t, please. And if I hit Control Enter, see, now I get 3.151. And I am off that little bit, and they will downgrade you for that. So anytime you're using that constant, or not that constant, but your rate of growth is what I'm saying, you must use your exact value of k, not your rounded. Use this. Do not use 0.220 when you are calculating how many things are left. Okay? From here, we'll come back tomorrow. We'll do a decay problem, and we'll go from there. Have a good day.